It's a pleasure to introduce Euripedes Carvalho da Silva from the Instituto Federal do Ceará, EFCE, Maracanã, Brazil. He finished his PhD at 2017 at University of São Paulo, and his thesis is on differential geometry, about existence of foliations on compact manifolds. And in the beginning of 2020, he started postdoctoral research at Federal University of Ceará under my supervision. And he started to work on geometric and metric aspects of singularities. And today, he's going to give a talk on this subject entitled Classification of Complex Algebraic Curves and the blow-spherical equivalence. Please, Euripedes, it's your turn.
Thank you very much for the presentation, Professor Edson. Good morning, everyone. I would like to thank you for the invitation. In this talk, I will speak about the classification of complex algebraic curves in the blow-spherical category. This work is in collaboration with Professor Edson Sampaio. This talk is divided in three parts: introduction and motivation, preliminaries, and main results. One of the mathematical most natural and important problem is the classifying objects in a given category. For instance, an important result of the classification in the classical theorem of the classification of compact surface under diffeomorphism. This is a classical theorem. This theorem, the topology determines, and it's determined by the genus and orientability. We consider X and Y two compact surfaces. Then the following equivalent statements are equivalent. The X and the Y are diffeomorphic. X and Y are homeomorphic. The true condition, X and Y are a blow-spherical homeomorphic. For condition, the orientable and genus is equals in this surface. In the non-compact case, this problem is very hard. The problem of classification in this case, we have the example. We consider X a plane, Y a cylinder, and Z the set. The surface X and Y has the same orientability and genus, but X and Y are not homeomorphic. In the condition B, the set X and the set Z, for example, are diffeomorphic, but they are not blow-spherical homeomorphic. These are non-compact case. In the singular case, in singular surface, in the setting of the singular surface in Euclidean space, the problem of classification is very hard as well. These two surfaces are homeomorphic, but are not blow-spherical homeomorphic. Okay. In this direction, in a seminal paper, Birbrae presents a complete classification for the germs of the semi-algebraic surface. The Birbrae consider a germ of semi-algebraic surface with isolated singularity and connect link. There is a unique rational number beta greater than 1, such that this germ is by Lipschitz homeomorphic with respect in a distance, in a metric, to a germ's beta horn. This set is a beta horn. And this theorem is in relation to the inner distance, okay? This is Professor Birbrae. It's a picture. Okay. Still in this direction of classification, we have a classification in the outer metric given by this theorem. We consider C1 and C2 two germs of complex curves. The following are equivalents. C1 and C2 have the same Lipschitz geometry. Condition 2, there is a homeomorphism of germs C1, C2, holomorphic except at 0, which is a by Lipschitz for the outer metric. Condition 3, C1 and C2 have the same embedded topology. And condition 4, there is a by Lipschitz homeomorphism of germs 8 of the C2 to C2 with 8C1 equals to C2. The important remark in this theorem is the equivalence of 1 and 4 with 3 were present by Neumann and Pichon. The equivalence of 2 and 3 was first proved by Fan and Tessier. Later, Fernandes present a geometric and elegant proof. In this picture, this is Professor Fan, this is Professor Tessier, this is Professor Neumann, Professor Pichon, and Professor Fernandes. Okay. The classification present in this moment are local. Now, we have a global classification on the complex algebraic curves. In this direction, Targino presents this theorem. Let C and gamma be two complex curves, algebraic curves, with reducible components CA and gamma J. The following are equivalents. C and gamma have the same Lipschitz geometry. Is equivalent the condition 2. That is isomorphism between the Lipschitz graph of C and gamma. This is a picture about the Professor Targino. Okay. Another global classification was presented by Fernandes and Sampaio. Now, is in a distance, okay? Consider X and Y semi-algebraic surface with isolate inner Lipschitz singularities. Then X and Y are inner Lipschomorphism if and only if the inner Lipschitz code are equivalents. Okay. Okay. Important information about this theorem: the code is the discrete invariant constructed by the authors. These invariants determine and is determined by the Lipschitz geometry. Okay. Okay. Now I will present some definitions and basic results necessary by defining the blow-spherical category. Okay, now first definition is tangent cone at infinity. Consider X a subset in Euclidean space and boundary semi-algebraic set. We say that the vector field in Euclidean space is a tangent vector of f at infinity, respectively at point P, if there are a sequence of points xi in the set X tend to infinity and a sequence of positive real numbers ti such that this limit equals v. This limit equals v. Let Cx infinity denote the set of our tangent vectors of x at infinity. We call this set the tangent cone of x at infinity. Okay. Now, let's present some examples of tangent cones. Consider M as smooth submanifold in Euclidean space, and X a point in this manifold. The tangent space equals to the tangent cone in the regular point. Okay? In this picture, it represents the tangent cone in this case. Okay. Another important example is the complex cusp. In this case, the tangent cone in a singular point, 0 in this case, is blue line. Blue line represents the tangent cone in the singularity. And red line represents the tangent cone at infinity in the set. Okay. Another way to present the tangent cone at infinity of the subset in Euclidean space is via the spherical blow-up at infinity. We consider the spherical blow-up at infinity, this map, rho infinity, in the cylinder to Euclidean space, given by this guy. Note that this map is a homeomorphism with inverse mapping this guy in the Euclidean space minus origin to the cylinder, given by this guy. Okay? Okay. Another important definition in this talk is the street transforms of the subset X under the under the spherical blow-up at infinity. The X prime infinity equals to the closed of the pre-image of this set. The subset X prime infinity intersection the sphere is called the boundary of the X prime infinity, is denoted by this guy, the boundary of the street transforms at infinity. Okay. In an important remark here, if X a semi-algebraic subset, then the boundary of the street transforms is equals to the intersection of the tangent cone at infinity with the sphere at infinity and a singular point or a regular point. Okay. Simple point. We consider X a subset in Euclidean space, D-dimensional subset, subanalytic set, for example. We say X in this guy is a simple point of this guy if there is an open subset in Euclidean space with X a point in this neighborhood, such that the connected components X1, X2, XR of this set are topological submanifold in Euclidean space with dimension of this component equals a dimension of the set. Condition B, this component in the boundary of the street transforms are a topological manifold with boundary. Okay. Now, S and P in the set be the set of simple points of this guy, and we define the real cone in the simple points over simple points. Let this function kxp to of the simple points to natural set be the function such that this function is the number of connected components of the germ. Okay. It is clean, the function is locally constant. In fact, this function is constant on its connected components xj in the simple point in this set. Then we define the relativity multiplicity of x at p to be kxp. This component equals to the function in a point x with x in this component, xj in this case. Okay, let x1, x2, xr be the connected component of the simple points. By reordering in this, if necessary, we assume that this inequality. Then we define this relativity multiplicity vector, this guy. In this picture, for example, we have the point P in the simple point. A green line represents the irreducible components. In this case, the relativity multiplicity is 3 because we have 3 components. Okay. Now I know the picture about relativity multiplicity. Again, the relativity multiplicity is the number of the leaves in this book. In this book, number of the leaves. Okay. Now, we go to remember the definition of degree of the complex algebraic set. We consider X a subset in Cn, P dimensional complex algebraic set, such that L is an element of the Grassmannian, such that L intersection tangent cone at infinity in 0. Let pi be the orthogonal projection such that the kern of this map is L. Therefore, there exists a proper algebraic set in CP such that D equals the cardinality in this guy, in this pre-image of T intersection the set X. This definition does not depend of T and does not depend of the L. Thus, we define the degree of X to be this cardinality, D. Okay. An example about degree. We consider this set, complex algebraic set. Now, we have the projection, orthogonal projection. This point T, the pre-image intersection the set in 2 points, in the point E, in the point F. Not consequently, degree of the set equals 2. Okay. Another important example is algebraic hypersurface in Cn. We consider X algebraic hypersurface, and let F be the expansion in the homogeneous polynomials. Then the tangent cone at infinities is the zero locus of FD. FD. Now, let FD be the composition of in reducible factors 8.1, 8.2, 8R. And this power, K1, K2, KR, is a relativity multiplicity. Okay. Now, we present the main definition of this talk. We consider X and Y be semi-algebraic sets in Euclidean space, respectively. Let P a point in the set and Q a point in the set, and a homeomorphism phi of this X to Y such that Q equals this limit is said to be blow-spherical homeomorphism at P if there are homeomorphism here, extend to a homeomorphism here in this set. Let X and Y be sets in Rn and Rm respectively, a homeomorphism 8 of the X to Y is said a blow-spherical homeomorphisms if is a homeomorphism blow-spherical for all points here. In this case, we say that the sets X and Y are a blow-spherical homomorphisms, homomorphic, or blow isomorphic. This proposition is a example, because we consider X and Y two sets in Euclidean space. If 8 of the X to Y is a semi-algebraic by Lipschitz homeomorphism between semi-algebraic sets, then 8 is a blow-spherical homeomorph. Okay. Now this proposition show that the relativity and multiplicity is invariant by blow-spherical homeomorphisms. More precisely, we consider X and Y semi-algebraic sets in Euclidean space. Let phi of the X to Y be a blow-spherical homeomorphism at P, then the relativity multiplicity in this point is equals to the relativity multiplicity in this point. In particular, the relativity multiplicity vector equals in this guy. Okay. This proposition shows that the tangent cone is invariant by a blow-spherical homeomorphisms. If 8 of the X to Y is a blow-spherical homeomorphism at P, then tangent cone of X at point P and tangent cone of Y in the point 8P are a blow-spherical homeomorphism at 0. The sketch of the proof this proposition, we consider this limit. This map 8P of the boundary of the street transforms into the boundary of the street transform is a homeomorphism by hypothesis. Let V8 this map be the homeomorphism satisfying this relation. Now we define this map in the tangent cone. Since this map is a blow-spherical homeomorphism at 0, and is finished this proposition. It's very, very easy, this proposition. Very simple, the proof. Okay. Now, now our first application of the proposition will be in differential geometry, more precisely, a type of Bernstein theorem. We consider X a subset in Cn, a complex algebraic set. If X is a blow-spherical regular at infinity, then X is a affine linear subspace in Cn, of Cn. X is a blow-spherical regular at infinity. X is blow-spherical regular a CD, a Euclidean space CD. Okay, that's mean. Okay. Since X is a blow-spherical regular at infinity, so X is irreducible in the first moment. By invariance of the tangent cone at infinity, we have X, tangent cone of X at infinity is a blow-spherical homeomorphic to CK. In particular, this cone is topological manifold. Now, by Prill theorem, the tangent cone of X at infinity is a linear subspace of Cn. Consequently, degree of the set equals 1. By invariance of the relativity multiplicity, we have this guy equals 1. Since degree of the set in this case is equal to the relativity multiplicity in this guy times degree of this cone, tangent cone, but equals 1. This product equals to 1. Degree of the set equals 1. Then X is a affine linear subspace of Cn. And I finished this proposition. Application to a Bernstein theorem. Okay. Okay. Now, we will define a complex blow-spherical tree using the next example, this complex algebraic curve. Okay. This complex blow-spherical tree is very important here. Okay. Now, the construction of the tree, I put a vertex C referring to the curves C here. And for each irreducible components of the curves, we put a new vertex, and we put edge join its vertex with equipaid with a weight given by the Euler characteristic. In this example, we have two components, irreducible components. C1, first irreducible component, C2, second irreducible components. These components, Euler characteristic is 1 in this guy. And the second irreducible component, Euler characteristic is 1. Okay, here. Now, for each singular point of this curve C, such that the singular point belongs to irreducible components, we add a new vertex with a label and add also a new vertex with label infinity, and we put edge join its such new vertex. Okay. in this example, we have two singular points. One singular point in this irreducible component, one singular point in this irreducible component, the join this guy, and infinity in this guy. Okay. In the singular point here, the irreducible components of the irreducible components of the tangent cone in this singular point, the number of direction in this point is 1. In this singular point, the number of tangent direction in this guy is 1. This guy. And the number of the tangent directs at infinity in this guy is 1. And join these guys. Okay. Here in this point of the tree, we consider the number of irreducible components tangent in this guy. In the put relativity multiplicity of the singular point here. Now we have the blow-spherical tree. This guy. It equals right side. Okay, equals construction. Okay. Now I will present the main result of this talk. The global classification of complex algebraic curves. We consider C and C tilde two complex algebraic curves where CA and C tilde J are the irreducible components of the curves C and C tilde, respectively. The following are equivalents. C and C tilde are a blow-spherical homeomorphic. Condition 2, there is a isomorphism between the complex blow-spherical tree, and condition 3, C and C tilde are strongly diffeomorphic. Strongly diffeomorphic is a diffeomorphism outside of the singular set and a blow-spherical homeomorphism. That's me. This proof of these theorems is very technical and not is more complicated. I don't present here. The complex blow-spherical tree determines and it's determined by the blow-spherical geometry. The complex blow-spherical tree see the number of the ends of the surface, the number of the directions and components tangent to the ends. The blow-spherical tree to see the topology of the surface, the genus, the Euler characteristic, and number of the tangent directs at singular point and at infinity. Here, some references. Thank you for your attention.